Hi, everybody. Our bell ringer question today is, at 1500 degrees Kelvin, our equilibrium constant is 1.6 times 10 to the fourth for the reaction C4 gas plus Cl2 gas yields CH3SCl gas plus HCl gas. At a given point in the reaction quotient with respect to pressure Qp is equal to 24.8. At this point, is CH3Cl or CH4 forming? So is the reaction proceeding to the right or to the left? All right, I hope you said that CH3Cl is forming because if you compare our reaction quotient to our equilibrium constant, Qp to Kp, you'll find that our reaction quotient is significantly smaller at this point in the reaction than our equilibrium constant, which means that we have more reactants. We have a larger number in our denominator than we do in our numerator. So we've got more reactants than we've got products. And that means that we need to proceed to the right to form more products to reach our equilibrium point. All right, we're going to be wrapping up how to solve equilibrium problems today. And we're going to tie our bell ringer into our lesson today as well, because sometimes when we're solving equilibrium problems, we need to first determine the reaction direction. So our learning objectives are, I can compare K and Q to determine the direction a reaction will proceed, and I can solve an equilibrium problem given a starting mixture of reactants and products. So up to this point, we've talked about only either being given our equilibrium amounts or being given starting reactant material. But what happens if we are given a mixture of reactants and products initially? So if our initial reaction system includes both reactants and products. In order to solve that type of problem, the first thing we need to do is determine the reaction direction. So whenever we have a mix of reactants and products, because we know that equilibrium is a dynamic system, if we have more product initially introduced into our chemical reaction, then we will have at equilibrium, we're going to see the reverse reaction, and that will change how we write the values in our ICE chart, in our reaction table. So that change row is going to be very important, and it's going to be determined by the direction the reaction proceeds. So when we're given a mixture of reactants and products at the beginning of our reaction, in order to determine the reaction direction, we need to compare our Q and K values. So we're going to initially look at our amounts, our starting amounts, determine our reaction quotient initially, and compare that to the equilibrium constant that we're given. If that value is larger or smaller, that will give us information and tell us how to proceed with the reaction. And it will therefore indicate the signs of X in our ICE chart. So if you think about that, if we have a small q, remember that means that we have a large number in our denominator, we have a large amount of reactants, a larger amount of reactants than we will have at equilibrium. That means our reaction is going to proceed to the right. And that means that we will have the typical orientation, the typical sign for our X's in our ICE table that we've used thus far. All of the reactions that we've looked at to this point have been reactions that proceed to the right. If, however, we have a Q value, our reaction quotient, that is larger than our K value, than our equilibrium constant, our reaction will proceed to the left. That means that we have more products than we will have at equilibrium. So that means that we need to see the reverse reaction. And if that is the case, what you will need to do is use the opposite sign in your change row. So if you have 1 mole of a reactant and then 2 moles of a product, but you've determined that your reaction is proceeding to the left, you have too much product, rather than putting a plus sign in front of the 2x in your product column for the change row, you would put a minus 2x because you're going to take your 2 moles of product and you're going to break them down into the reactants to achieve that equilibrium, that equilibrium constant, that equilibrium ratio. So, what does this look like in practice? Basically, it looks like solving an equilibrium problem in ways that we've done it up to this point, but we're just adding that one more step of comparing Q and K. So let's take a look at a practice problem. We have PCl5 gas that's degrading down into PCl3 gas and Cl2 gas at a temperature of 250 degrees. We're given our initial concentrations for our reactant and both of our products. So we are starting with a mixture of reactants and products. And we're given the volume of our container as well as our equilibrium constant. Our Kc is 4.2 times 10 to the negative second. The first question we need to answer is, in which direction will this reaction proceed? In order to answer that question, we need to compare Q to K. We need to compare our reaction quotient to our equilibrium constant. And in order to write an equilibrium constant, we need to convert all of our amounts into molar concentrations. So I will do that. Pause the video, check back in just a second to make sure that your calculations are correct. So here you can see I've calculated the molar concentration of PCl5, and because the concentrations of PCl3 and Cl2 are equal, I've only done one calculation there. That means that we can plug our values into our reaction quotient. And that will look something like this. 0.0900 times 0.0900 divided by 0.2100. When we simplify that, what we see is Q, or our reaction quotient, is equal to 3.86 times 10 to the negative second. And we can now compare our reaction quotient to our equilibrium constant. And as we can see, 3.86 times 10 to the negative second is smaller than 4.2 times 10 to the negative second. And based on what we know about the comparisons of Q and K, this will tell us the direction that our reaction will proceed. Based on our calculations, in which direction will this reaction proceed? The reaction will proceed to the right. I'm going to do a little bit of erasing and set up an ice chart so that we can get started on calculating our equilibrium concentrations. Knowing that our reaction will proceed to the right, that means that we can use the standard signs for X that we have been. We're going to use a negative X for the change in our reactants and a positive X for the change in our products. So let's plug our values into our ice table and then get going. So now I can fill out my equilibrium row. I have 0.2100 minus X and 0.0900 plus X and 0.0900 plus X. Because I have been given my equilibrium concentration of PCl5, I can use this value combined with this expression to solve for X. And when I solve for X, that will allow me to then calculate the concentration of PCl3 and Cl2 at equilibrium. So first things first, I'm going to solve for X and then plug that value in to solve for my remaining concentrations. I'll do that. You can check back in just a minute. Pause the video right here. So when you plug all those numbers in, you find that X is equal to 0.0035 and the concentration of PCl3 is equal to the concentration of Cl2, which is equal to 0.0900 plus. It's very important to pay attention to your signs here. 0.0035. So those concentrations are 0.0935 molar at equilibrium. So when solving equilibrium problems, there's a couple of basic steps. When you're setting up to solve an equilibrium problem, it's a good idea to write your reaction quotient. So remember, that's the ratio of products to reactants, raising everything to the power of the coefficient, the stoichiometric coefficient. You should make sure that your equation is balanced. When you're solving equilibrium problems, there's a couple of steps to remember. When you're setting up, make sure your equation is balanced. It's a good idea to write out your reaction quotient. So that's your Q value, your ratio of products to reactants. And then make sure that you're using the correct units. Make sure everything is either in atmospheres if you're using pressures, or it's in molarity, moles per volume, if you're doing concentration. Then set up your reaction table. Determine your reaction direction by comparing Q to K. So that will determine what your signs for X are, and then construct and fill in your table. Finally, you can solve. Substitute your quantities into Q, so use your equilibrium quantities or solve for a particular X. So you are able to plug that in and solve all of the remaining unknown values. And when it's appropriate, when you're solving, you can assume that X is negligible. And there you have it, how to solve equilibrium problems.